Well, hello everyone. Welcome to part 10 of my DLL injection into all processes video. And today we will continue coding our Windows driver, and I will continue writing DLL injection via Kernel APC. So without any further delays, let's load up our Visual Studio. And again, I'm working with Visual Studio 2019 and inject all solution. So if you remember, we left it off on these procedures for the normal routine, for the kernel routine, and rundown routine. And if you recall, three types of callbacks that are invoked by kernel APCs. Again, watch the previous module if you want to review all that. Also, make sure to check my blog post. If you go to dennisbabkin.com and then blog and then search for Kernel APC. Oops, not the tag, I'm sorry. If you go here and do Kernel APC, and you spell it right, depth of Windows APCs. Then if you scroll a little bit down where it says General APC Internals, if you click on Inside NT Asynchronous Procedure Calls, here's a long article here that will describe what kernel APCs are. So what we did, we also coded a small assembly file with 3 functions that basically provided us a safe jump into dereferencing object at the end of our APC callback. Now, the description here kind of like explains what it is. Please watch the previous video where I explained why we need this jump. Basically, this is so that we do not return back when a driver can be unloaded when we call this API. So we're not supposed to come back. So in case we had a call here, and if we returned, well, this memory might not be available. So we did not want to create a race condition. That's why we just jump into this function and do not return back. So we wrote 3 kind of like stubs for, let's see, what is it called? Rundown routine, for kernel routine, and then for a normal routine. Okay, and all of these routines would call our procedure kind of like a C++ procs that would return true to dereference our driver, or would return false not to do that. Now we coded our x86. Now let's see if it compiles. We did this before. Now let's try it again. And it does. Now let's switch to release, and let's make sure that that compiles. We have to check that so that we don't have to come back and deal with broken functions. Okay, so if we go back to debug and go to x86, what we need to do is write our 32-bit version, because unlike 64-bit, we haven't written it yet, and that is the kind of like, I'm not going to say downside, but this is definitely a difficulty of coding in assembly, because you actually have to write it for any specific bitness of the CPU that your code may be running on. But at least we know what to do, so let's do it real quick. So first, it's just some basic scaffolding for the ASM file. This is just like from a long time ago. I'm not going to explain all the stuff. Okay, so first let's do the rundown routine, and let's copy it here. I'm going to copy it with the comment, even though the comment would not be valid. And then at the end we have and p, and we need to put and so that ASM didn't complain. Okay, now if you look, now for x86, the calling convention did not really matter, because by default it was all fast call. In other words, parameters were passed on registers and then on the stack, if 4 was not enough. But for x86, this actually matters. So what this means is that parameters are passed to us on the stack, and the callee cleans the stack. So this is kind of like the convention that we have to follow. what we also have to follow is the name mangling. Now, this is what has to be done. Now, look up name mangling or name decoration for STD convention. Basically, what happens is not STD convention, for a standard call convention. So basically what happens is that we have to prepend it with an underscore, then we have to put @ and then the number of bytes that are passed to it into parameters. And the parameters are passed on the stack, and it would be ESP plus 4. We get a pointer to our KAPC. And so that is the difference. Okay, so, and then we basically have to do the same thing. We need to, let's just copy it from here. Need to call our rundown procedure. And if we look at it, let's just like search real quick for it. So let me copy it. Now in this case it does matter for us. So I'm going to copy it right here. Again, it's std call, so it means that we have to do this and add 4, because again, that's how this procedure is declared. And what we need to do, we need to pass its argument on the stack, which we got from over here. Now, passing it on the stack is not as easy because we have to push it down from this location. And before I forget, what we need to do, we also need to declare it over here as our extern procedure, so that compiler knows that it's coming from the outside. Okay, now let's take a look how we can push this parameter so that it can be used in this function. So I threw in a quick diagram here just to show what I am trying to accomplish next. So right here on the left is the breakdown of the stack as we have it when we enter the rundown procedure over here. I'm sorry, rundown routine. So the ESP, the stack pointer at the top, has the return address from the procedure, obviously, so that we can return. And then, next cell, which is 4 bytes lower, again, this is next D word, we have our parameter, which is pointer to KAPC, which we get here by definition from the function call. Okay, now when we call this rundown routine, we basically advance the pointer back by 4 by D word, and that will put us the return address for the rundown routine here. But what we need to have is the KAPC parameter that we can pass into rundown routine procedure, because that's the way it is designed here. I mean, we have to pass it to it. So the easiest thing to do is to swap these two parameters, because again, at the end, we will still need the return address from our procedure to be over here. So if we swap them around, you see like what I did here, 4 to 0 and 0 to 4, we will achieve our goal. So let's code it before we actually call our function. And let's just say move parameters for the forwarded call to function and push back return address, because again, we obviously need return address. So we will use EAX, which is a scratch register. We take it from ESP. And then to exchange, we would use this exchange instruction, and we would do +4 EAX, and then to complete, we put EAX back into ESP. Now again, it's not the same EAX because we actually exchanged it with ESP at 4. And what this does is literally just switching these two around, right? So if you look at it, that's it, this puts here and this puts there. So that's what we accomplish with this little exchange. And yeah, so then we get the result. Then we, well, I'll just copy it from, sorry, not from there, but from here. Then we act depending on the return value. Now in here we don't have REX, we have EAX, or 32-bit value. And come on, I just can't type at all. Okay, so if we get 0, we just return. Okay, and what we have left is just add this call to this function that will dereference our driver object. Now, obviously this would be ECX. And let's see, we need to declare this as external dword, because again in 32-bit it will be dword. And we also need this function. Okay, now we need to write here, actually right here, if we go into IC and put this function here just to see how it's declared, if we go to the peak definition, you see that it is declared via fast call, which is important for us. Again, like you see fast call. So we need to document it in assembly here. And let's say info is declared as fast call calling convention. And the reason being, we need this to be able to actually decorate this. Now in this case, for the fast call calling convention, we put underscore before, underscore after, and then number of bytes that we are passing. And since we're passing ECX, that would be 4. And since we declared it as such, again, we are declaring it with the imp. And if you want to know what that imp is, you can go, let's see, into my blog, and you can search by underscore imp, and basically 2 blog posts, intricacies of Microsoft compilers, the case of Curious Imp, and also part 2 that will explain what this imp is for. And I again explained this in my previous video, basically to avoid the small stub, jump stub that compiler adds. And this is also a dword because it's a reference in IAT, import address table. And here you go. Let's just add a little comment here and just say name decoration for the fast calling convention, in case people are wondering, you know, what are these weird symbols here. Okay, so we got here, and that should be it. Now, what is important to note, guys, is what is happening with the stack that we are pushing here with the values. Now, if we take my diagram, let's see, where is it? So as you can see before, what we did, we basically swapped this value with this value. So inside the rundown routine procedure, the stack looked as such, like right here. But what is happening with this parameter? Because, you know, you would think when we return, this would be pushed out, would be popped. But then we have this. So how are we going to return? Because as you can see, we're just doing, let me just scroll down a little bit. Because all we're doing, we're just like returning, we're checking, then we either return or jump, which is kind of like the same thing. So what happens with this parameter? Well, this parameter is actually pushed out or popped from the stack by rundown procedure. I keep calling it rundown routine procedure. And the reason being is that the rundown routine procedure is declared as standard call. And what this means is that, obviously, yeah, its parameters are passed on the stack, but this also means that this procedure has to take care of the stack itself, or it has to pop them, okay? And that's what this procedure is doing. And you might ask, why are we not doing it? Because we are also standard call. Well, because we're coding in assembly, we can simply pass it on to this procedure. So this is kind of like a neat trick for us to do. And that's why we're not worrying about, let's see, about this parameter here. Because again, it will be taken care internally by this function. And what is important for us is obviously to declare it as a standard call, which we did. If you look, you see like pretty much all of them, I made sure that I declared them as standard call. Okay, so that's about our rundown procedure. So the next one, let's take a look in the 64-bit, because again, it's easy for us. We can just copy and paste it from over here. It's a little bit different calling convention, so we have to do a little bit different stack manipulations here. Okay, now the rundown, the kernel routine procedure also is standard call, so we have to prepend it with underscore at, and then we have to calculate how many parameters it receives. Well, it's 5 times 4, so it's 20. Okay. Now, then we also need to declare it. Oh no, I'm sorry, we don't need to declare anything. We need to rewrite these things, because obviously they're not registers, and these are passed on the stack, and pointers will be different. So I'm just going to do quick, oops, not here, quick formatting. And the way you can kind of tell, let's see, so the first one is 4, then we have 8, then we have C, then we have 10 and 14. Now these are hexadecimal numbers. I know it's kind of confusing with the C one, but they're kind of easy here. They just, you know, reiterate like this. And yeah, so that's how our layout is. That's how we get our parameters. And we need to do exact same thing here, except that we have more parameters to actually work with. You know, guys, since I drew that little diagram before this one, let me copy and paste it into the source code so that you can actually see it. And what I will do, I will paste it right here. Oops. Right under, so that we can refer to it later, because again, I just don't want to delete it. And that's what explains this stuff. And let me do the same thing for these parameters. So guys, the goal is very simple. Let me show you real quick. So basically, this is how, on the left, this is how ESP would look like when we just step into kernel routine here. And again, first is return address from it. Then we have all of our pointers to our parameters as are defined here. As you see, I just copied it here. And then when we call our kernel routine procedure, we basically have to shift it down, or up in this case, by -4, by 1 D word. And that's how the layout would be for our kernel routine procedure, which obviously takes the same parameters. So what we need to do, we just need to shift them up and take this kernel address from, return address from kernel routine and put it over here. And then because our kernel routine procedure is declared as standard call, it will pop all of these parameters here off the stack, and then all that we would have left is the return address from our kernel routine. Okay, so this is the kind of like basic premise what we will be doing here, and it's just a little bit more, moving here. So what we do, we take EAX from the first value and push it at the very back. So again, if let me just bring the diagram back. Right, so we take it from here and we put it here. So that's what this exchange does, kind of like so. But because we will be doing them one by one, we will be slowly kind of bubbling them up. So let me just show you what I'm talking about, and then I'll show it again once again. So that pushes all the way up, I mean down, and then we go here, and then let me just erase them. So it will be 10, then we go C8, 4, and here. So 10, C8, 4, and then we push this one to, move this one to just ESP0. So just to show it once again, as you can see, we read one here, we exchange it with this one, then we take this one and exchange it with this one, so it's kind of like pushes them up one by one. So eventually, if you look at this, little manipulation here, we would get this layout. So I'm not going to go one by one, but you can kind of tell what's going on. And again, let me just copy the whole thing, and I'm going to paste it here so that we can refer to it later. Let's see if I can just do it like so. Okay, so we did this. We basically prepared the stack, and then we kind of do the exact same thing as we did here. Let me just do copy and paste and make sure that I don't screw anything up, because parameters are not the same. So we have kernel procedure, not rundown, and we do this. And by the way, this is not how it's declared, so we need to go and look up kernel routine procedure. Hey, oops, come on. Wrong button. Okay, so this is how it's declared. Again, with all of these parameters. So then we call kernel routine 20. And then act depending on the return value. And obviously, if it's 0, we return. Or otherwise we just dereference our object, so that should be fine. Let's save it. Okay guys, and then one last thing here, we need to do the same with our normal routine. No, hold on, what's going on here? There's a little bit of a problem here. Oh, by the way, kernel routine. It's pretty stupid to put it over there. So we go here, and then we have end p, just to conform with assembly semantics here. Okay, so by the way, we need to put this in here. Again, it has to match the name of the function. Okay, and I'm gonna apologize. You were probably screaming at me that I didn't do this in the beginning. Okay, so 20 means that we have 20 bytes that are passed in. Okay, over here, let's count how many bytes do we have. First of all, let's delete this. And then we have ESP plus. And the reason I'm putting this elaborate comment is so that we can actually, work easier by just looking at it with this stuff. Okay, so we have, obviously it's standard call, and we have 12 bytes, which is 3 times 4. And what we need to do, we need to put the AND for this procedure, which I haven't done before. Okay, so we get this call, we get these parameters, and I'm not going to draw it, guys, but pretty much have to do the same thing here. We need to push the stack basically values up, and what we have is just 3 parameters, so just really simple: C, 8, 4, and 0. So kind of the same thing. Again, I'm not going to waste your time. And then we need to call, well, we need to do all this. Yeah, let me see and make sure I don't screw it up. Okay, so what we are calling is NormalRoutine. And need to delete that. And need to remove that because it will be a different name. And let's go look up NormalRoutine. And it's a little bit smaller, so let's copy its declaration here. And again, it's standard call and 3 parameters, 12 bytes. And here we basically check EAX and return. Okay, I think at this point we are good. So let's see if this thing compiles. And let's see now, what do we have here? 2 errors. Now, okay, well, we obviously did not declare them as external procedures. So we need to go here and declare them so. And then we need to do this and declare it so. Okay, and let's see, one unresolved parameter. Now, extern D word. Now, why is it not? Oh, because I also have to put underscore. Again, that's just this calling convention in C that messes me up. And hey, obviously, you know, I changed it here, but I didn't change it in 3 places. Didn't change it in 3 places where it's used. That's kind of silly. Now, x86 was way more difficult, you know, type of assembly. That's why they changed it, so we don't have to deal with all these underscores and things. And I understand why people don't want to code in assembly, so it's kind of tedious. And look at that, it actually compiled. And let's do x86. And this one did not compile. Let's see what the problem is. And we don't have safe SEH, structured exception handling. Now it's easy to fix. We go to ASM32, go into properties, we go into advanced, and we enable it right here on this file. Let's try to rebuild it. Okay, so now it works. Let's switch back to 64-bit debug mode. And at this point, we have these little stubs that would call our procedures here. Again, I explained why I was doing it, so that we can call this dereferencing object safely. And so right now we have our functions that we can start calling. Now, guys, I understand that that was a lot of code, and I went through it very, very, you know, kind of slowly and methodically. This is a link right here that you can actually use to see why I was doing this. Again, it explains it with more details, so please read it. And at this point, we can actually go into implementing our further code.